The first problem is the wavelength of H alpha line for hydrogen is 656.28 nanometer. What is the wavelength of H alpha line for deuterium? In the present problem, the wavelength of H alpha line for hydrogen is given. From that data, we have to find out the wavelength of H alpha line for deuterium. What is the H alpha line transition? It is a transition from Ni is equal to 3 to Nf is equal to 2. And remember, for hydrogen atom, the nucleus contain proton only, and for deuterium, the nucleus contain both proton and neutron. First, let us write the wave number corresponding to the H alpha line transition. This is equal to 1 by lambda, which is equal to Rz into 1 by 2 square minus 1 by 3 square. And this is equal to Rz, which is the Rydberg constant, into 5 by 36. Now what is Rz, the Rydberg constant? This is equal to mu e raised to 4 z square divided by 8 epsilon 0 square Ch cube, where mu is the reduced mass. Now let us analyze the problem for hydrogen and deuterium separately. Now for hydrogen atom, we can write 1 by lambda h, that is the wavelength corresponding to H alpha line transition. 1 by lambda h, that is equal to mu h e raised to 4 divided by 8 epsilon 0 square Ch cube, where mu h is the reduced mass. Mu h is the reduced mass for hydrogen atom. Now for deuterium, let lambda d corresponding to the H alpha line wavelength, then 1 by lambda d is equal to mu d e raised to 4 divided by 8 epsilon 0 square Ch cube into 5 by 36. What is mu h? Mu h is the reduced mass of hydrogen, that is mass of proton into mass of electron divided by mass of proton plus mass of electron, because the mass of hydrogen nucleus is mass of proton. Now in the case of deuterium, the reduced mass mu d is given by 2 times mass of proton into mass of electron divided by mass of 2 times mass of proton plus mass of electron. This is because the mass of deuterium nucleus is approximately equal to 2 times mass of proton. We have to find out the wavelength of H alpha line for deuterium, that is we have to find out lambda d. From the above equation, we can see that lambda h by lambda d is mu d divided by mu h, or lambda d. Lambda d is the wavelength of H alpha line for deuterium, that is lambda h into mu h divided by mu d. Now using this equation, you can find out the wavelength of H alpha line for deuterium if you know the reduced mass of hydrogen and deuterium. Also, lambda h is given in the question. Let us find out what is mu d by mu h. What is mu d by mu h? Mu d by mu h is 2 times mass of proton into mass of electron divided by 2 times mass of proton plus mass of electron. Now whole divided by mu h. What is mu h? It is mass of proton into mass of electron, mass of proton into mass of electron divided by mass of proton plus mass of electron. Let us simplify this expression. You will get mu d by mu h is equal to 2 times mass of proton plus mass of electron divided by 2 times mass of proton plus mass of electron. Now let us take mass of electron outside the bracket and let us simplify this expression. You will get the answer as 2 times 1 plus mass of proton by mass of electron divided by 1 plus 2 times mass of proton by mass of electron. And we know that mass of proton divided by mass of electron is equal to 1836. Mass of proton is 1836 times the mass of electron. Now use the relation, you will get mu d by mu h, that is equal to 2 into 1 plus 1836 divided by 1 plus 2 into 1836, and this is equal to 1.002723. Therefore, we can say lambda d, which is equal to lambda h divided by mu d by mu h. You can write like this. Lambda d is lambda h divided by mu d by mu h. Therefore, we can say that the wavelength of H alpha line for deuterium lambda d is equal to, lambda h is already given in the question as 656.28 divided by 1.002723, and that is equal to 656.10 nanometer. The next problem is, a carbon atom has its electrons with configuration 1s2, 2s2, 2p, 3p. List all expected terms on the basis of LS coupling scheme. We have, in LS coupling scheme, capital L is equal to sum over small li, capital S is equal to sum over small si, and J is equal to capital L plus capital S. Here we have to use the term symbol notation, and it is given by 2s plus 1 Lj. In the present problem, the carbon atom is in the excited state 1s2, 2s2, then 2p1, 3p1. Now, for the single 2p electron, we have L1 is equal to 1, and for this 3p electron, we have L2 is equal to 1. Now, according to LS coupling scheme, L is equal to sum over Li, and this capital L can take the value modulus of L1 plus L2 to L1 minus L2. That is, here L1 is equal to 1, L2 is equal to 1. Therefore, capital L can take the value from 1 plus 1, modulus of 1 plus 1 to modulus of 1 minus 1. That is, the value of L is 2, 1 and 0. That is, the carbon atom which has an angular momentum L, which can take the value 2, 1 and 0. Now for 2p electron, you have S1 is equal to 1 by 2, and for 3p electron you have S2 is equal to 1 by 2. Therefore, capital S, which is equal to sum over Si. Now this S can have the values S1 plus S2 to S1 minus S2, modulus of S1 plus S2 to modulus of S1 minus S2, and we can say that the capital S is equal to modulus of 1 by 2 plus 1 by 2 to modulus of 1 by 2 minus 1 by 2. That is, capital S can have the value 1 and 0. That is, the spin of the carbon atom is 1 and 0. Now let us write the term symbol. For first, let us use 3 columns. L for L, S and J. We have L is equal to 210, S is equal to 10. Now when L is equal to 2, S is equal to 1. When L is equal to 2, S is equal to 1. We have the value of J is 3, 2 and 1, because J can have the value L plus S to L minus S modulus of And when L is equal to 2, S is equal to 0, the value of J is 2. When L is equal to 1, S is equal to 1, the value of J is 210. Similarly, when L is equal to 1, S is equal to 0, the value of J is 1. And for L is equal to 0, S is equal to 1, the value of J is 1. Therefore, for the first term, when S is equal to 1, J is equal to 3 to 1, the term symbol is 3D1, 2, 3. We can write it as 3D1, 3D2, 3D3. When S is equal to 0, J is equal to 2, we have the term symbol 1D2. When S is equal to 1, J is equal to 210, we have the term symbol 3P210, that is 3P2, 3P1 and 3P0. When S is equal to 0, J is equal to 1, the term symbol is 1P1. And when S is equal to 1, J is equal to 1, the term symbol is 3S. The term symbol is 3S1. And when S is equal to 0, J is equal to 0, the term symbol is 1S. The next problem is draw the Zeeman pattern for the transition 6, 1D2 to 5, 1P1 of cadmium atom. In the present problem, we have to draw the Zeeman pattern corresponding to the given transition of cadmium atom. Since cadmium atom is given, it is evident that the pattern corresponds to normal Zeeman effect, because in cadmium atom there is 2 valence electron and the total spin is 0. Therefore, if you put a cadmium atom in an external magnetic field B0, the energy level will split up into 3 components and the corresponding pattern is normal Zeeman pattern. Let us draw the energy level diagram corresponding to 6D12 and 5,1P1. For 1D2 level, we know that the value of L is equal to 2, because D corresponding to L is equal to 2, and for 1P1 the value of L is 1, and this energy level diagram corresponding to the zero magnetic field. When the magnetic field is applied, the energy level will become E0 plus mu B B0 ML. That is, depending upon the value of ML, the energy level will split. Now for L is equal to 2, ML can have 2L plus 1 values. ML can have 2L plus 1 values. That is, for L is equal to 2, we have 5 levels corresponding to ML is equal to -2, -1, 0, +1 and +2. When you switch on the magnetic field, L is equal to 2 level split into 5 component with ML is equal to 2, 1, 0, -1 and -2. This is because ML can have 2L plus 1 values, therefore energy can also have 2L plus 1 values. Now, when you switch on the magnetic field, L is equal to 1 level will split up into 3 components, because 2L plus 1 is equal to 3. That is, the value of ML is here 1, 0 and -1. 1, 0 and -1. L is equal to 1 level split up into 3 components in the presence of magnetic field. That is, ML is equal to 1, 0 and -1. And in between this level, the transition happens, and that leads to the normal Zeeman pattern. For that, we should know what is the selection rule. Selection rule is delta L is equal to plus or minus 1, and delta ML is 0 and plus or minus 1. First, let us draw the transition that corresponding to delta ML is -1. Now, in all the transition, the value of delta L is 1. So, it is satisfied. The first 3 set of transition corresponding to delta ML is equal to -1. Now, let us draw the transition corresponding to delta ML is 0. That is from -1 to -1, 0 to 0 and 1 to 1. these three transition corresponding to delta ml is equal to 0. Now again there is three more transition that corresponding to delta ml is plus 1, that is from 0 to minus 1, 1 to 0 and 2 to 1. These transition corresponding to delta ml is equal to plus 1. So there is actually 9 transition, but we will get 3 spectral line because for delta ml is equal to minus 1, all the transition corresponding to delta ml is minus 1 will appear as a single line, and delta ml is equal to 0 appear as another line, and delta ml is equal to plus 1 will appear as another line. For delta ml is equal to 0 transition, the position of the spectral line is at nu 0, and for delta ml is plus 1, the position of the spectral line is at nu 0 plus EB0 by 4 pi m, and for delta ml is minus 1, it is at nu 0 minus EB0 by 4 pi m. The next problem is define Landé G factor and obtain the equation for Landé G factor in terms of angular momentum. Here we have to define Landé G factor and we have to obtain an equation for Landé G factor. The Landé G factor Gj describes the ratio of the magnetic momentum mu j of the particle and total angular momentum j as mu j by j is equal to minus gj e by 2m. The Landé G factor relates the magnetic momentum mu j and total angular momentum j by the equation mu j by j is equal to minus gj e by 2m. Suppose you have an electron which is placed in a magnetic field, then the interaction energy is given by minus mu l plus minus of mu l plus mu s dot b0, where mu l is the magnetic moment due to orbital motion and mu s is the magnetic moment due to spin motion. We have mu l is equal to minus e by 2m into l and mu s is equal to minus e by 2m into s into 2. Therefore, the interaction energy is e by 2m into l plus 2s dot b0. Let it be our equation number 1. Now, due to LS coupling, L and S coupled together to form J, we can say that in the exactly opposite direction of J, you have a vector called mu J, which is the magnetic moment due to magnetic moment due to total angular momentum. Therefore, the interaction energy can be written as minus mu j dot b0. Now, what is mu j? Minus gj e by 2m into j. Therefore, delta E becomes E by 2m Gj J dot B0, where Gj is the Landé G factor. Landé G factor. Now, from 1 and 2, we can say that L plus 2s, vector L plus 2s is equal to Gj J. This is the first very important equation we are obtaining. Now take the dot product with a j on both sides. We will get j dot L plus 2s is equal to gj j square. We know that j is equal to L plus s, therefore L is equal to j minus s. Therefore L plus 2s become j plus s. Therefore LHS become j dot j plus s, that is equal to gj j square. Now this is equal to j square plus j dot s, that is equal to gj j square. Now take the square of L, that is L square is equal to j square plus s square minus 2 times j dot s. Therefore j dot s becomes j square plus s square minus L square divided by 2. Hence our equation becomes j square plus j square plus s square minus l square divided by 2 is equal to j square. We know that from the quantization principle, j square is equal to j into j plus 1 h bar square, l square is equal to l into l plus 1 h bar square, and s square is equal to s into s plus 1 h bar square. Now substitute these values. We will get j into j plus 1 h bar square plus again j into j plus 1 h bar square plus s into s plus 1 h bar square. Let us rewrite this. We have j square is equal to j into j plus 1 h bar square plus again j into j plus 1 h bar square plus s into s plus 1 h bar square minus l into l plus 1 h bar square divided by 2 is equal to gj into j plus 1 h bar square. H bar square will cancel on both sides, so you will be left with gj minus 1 into j plus 1, gj minus 1 into j plus 1, that is equal to j into j plus 1 plus s into s plus 1 minus l into l plus 1 divided by 2. Therefore, the Landé G factor gj is equal to 1 plus j into j plus 1 plus s into s plus 1 minus l into l plus 1 divided by 2j into j plus 1. The next problem is the electronic configuration of magnesium is 1s2, 2s2, 2p6, 3s2. Obtain its ground state term. In the present problem, the electronic configuration of magnesium is given. It is 1s2, 2s2, 2p6, 3s2. We have to obtain the ground state term. Let us use the term symbol 2s plus 1 Lj, where s is the total spin of the atom, L is the orbital angular momentum, and J is the total angular momentum. Now you consider the valence s electron. For the valence s electron, which is completely filled, for the first electron, ms is equal to plus half, and for the second electron, ms is equal to minus half. Now, if you consider magnesium atom, the capital Ms, that is equal to sum over small ms, that is equal to 1 by 2 minus 1 by 2, which is equal to 0. When capital Ms is equal to 0, it is evident that capital S is also 0, because Ms can take only 2s plus 1 value, and here for s is equal to 0, the value is 0. That is, when ms is equal to 0, we can say that the capital S is also 0. Now, both electrons are in S subshell, so we can say their L is equal to 0 in both electron. Therefore, for both electron, Ml is also 0. Now, what is capital Ml for magnesium atom? For capital Ml, that is equal to sum over small ml, and that is equal to 0 plus 0, that is equal to 0. When capital Ml is equal to 0, it is evident that capital L is also 0, because capital Ml can take only 2L plus 1 value, and that value is 0 here. Now, what is J? J is equal to L plus S. Since L and S are 0, J is also equal to 0. Now, let us write the term symbol. What is the multiplicity 2S plus 1? When S is equal to 0, our 2S plus 1 is 1, and L is equal to 0 means it corresponding to S, capital S, and J is also equal to 0. Therefore, the ground state term symbol 2S plus 1 Lj becomes 2 into 0 plus 1. Then L is equal to 0 corresponding to capital S. Then 0, that is 1 S 0. The next problem is compute the energy of the K alpha X-ray of sodium Z is equal to 11. The measured value of energy is 1.04 kilo electron volt. Comment on the result. We know that for K alpha X-ray, the frequency is given by 3 by 4 RC Z effective square, where Z effective is the effective value of Z, which is given by Z minus sigma, where sigma is the screening constant, and for K series, the value of sigma is equal to 1. Now, what is the energy of K alpha X-ray? For K alpha X-ray, the energy can be written as h nu, that is equal to h times 3 by 4 RC Z effective square. Now this implies that h nu is equal to h, that is 3 by 4 HRC. What is Z effective? It is Z minus sigma square. Now again we can write h nu is equal to 3 by 4 HRC Z minus 1 square, because the screening constant is 1 for K series. It is given that Z is equal to 11. Therefore, h nu is equal to 3 by 4 HRC 11 minus 1 whole square. Now let us compute the value. 3 into 6.626 into 10 raised to minus 34 into R is a Rydberg constant, 1.097 into 10 raised to 7 into 3 into 10 raised to 8 into 10 square divided by 4. This is equal to 1.635 into 10 raised to minus 16 joule. Here we have obtained the energy in joule. Let us convert it into electron volt. 1 electron volt is 1.602 into 10 raised to minus 19 joule. Therefore, h nu is equal to 1.635 into 10 raised to minus 16 divided by 1.602 into 10 raised to minus 19 electron volt. 1.602 into 10 raised to minus 19 electron volt. Therefore, h nu is equal to 1.020 kilo electron volt. That is, our result is 1.020 kilo electron volt, which is the computed energy of K alpha from the given data. But it is given that the measured value of energy is 1.04 kilo electron volt. That is, there is a discrepancy from the theoretically calculated value and the measured value. Why this discrepancy happens? This discrepancy may be due to the correction in screening constant. We have assumed that the value of sigma is equal to 1, and which may not be correct. The next problem is obtain the expression for rotational energy of a rigid rotator and show that the energy depends on the quantum number J. In the present problem, we have to find out an expression for the rotational energy of a rigid rotator, and we have to prove that this rotational energy depends upon the rotational quantum number J. We know that the rotational kinetic energy is half I omega square. The rotational kinetic energy is half I omega square. Now we can write it as L square by 2I. This is because L is equal to I omega. Now according to quantum mechanics, L is quantized. Therefore we can write L is equal to root of J into J plus 1 H cross, where J is the rotational quantum number. That is, the angular momentum of the molecule is quantized according to quantum mechanics. Therefore, we can say E rotational, that is equal to J into J plus 1 H cross square divided by 2I, or we can say Ej, that is equal to H by 2 pi whole square, then J into J plus 1 by 2I. Now we can write it as H square, that is Ej is equal to H square divided by 8 pi square IC into Ej is equal to H square by 8 pi square I into J plus 1 joules. That is, the rotational energy depends upon the rotational quantum number J. The next problem is the average spacing between adjacent rotational lines of CO molecule is 3.8626 centimeter inverse. Calculate the length of CO bond. In the present problem, the average spacing between adjacent rotational lines of CO molecule is given. We have to calculate the length of CO bond. We know that the spacing between adjacent rotational line is 2b. Once we have b, we can calculate the moment of inertia using the equation I is equal to h by 8 pi square bc. In the present problem, 2b is given as 3.8626 centimeter inverse. Therefore, the rotational constant b is equal to 1.9313 centimeter inverse, and that is equal to 193.13 meter inverse. Now let us calculate the moment of inertia as h is equal to h by 8 pi square bc. That is equal to 6.626 into 10 raised to minus 34 divided by 8 pi square into 193.13 into 3 into 10 raised to 8, and that is equal to 1.448 into 10 raised to minus 46 kilogram meter square. This is the expression for the moment of inertia. Now take the mass of carbon as 12 AMU and mass of oxygen as 16 AMU. Now let us calculate the reduced mass of CO, that is MCMO divided by MC plus MO into 1.66 into 10 raised to minus 27 kilogram, and that is equal to 12 into 16 divided by 12 plus 16 into 1.66 into 10 raised to minus 27 kilogram, and this is equal to 1.138 into 10 raised to minus 26 kilogram. Thus we have evaluated the reduced mass and also the moment of inertia. Now let us find out the bond length R, which is equal to root of I by mu, and this is equal to 1.448 into 10 raised to minus 46 divided by 1.138 into 10 raised to minus 26, and this is equal to 112.80 into 10 raised to minus 12 meter, or R is equal to 1.13 angstrom. This is the bond length.